Hello friends, I'm Jagdish Perk Associate. Today's topic is strength of materials. So in strength of materials, I'll be solving a numerical problem. And this numerical problem was appeared in the IES paper 2004. So in this video, you will be seeing the solving method of this numerical problem. Okay. So before going to this video, please press the subscribe button of our channel, the Mechanical Engineers team, and also click the bell icon so that you will get the notifications for new videos. Okay. So let's begin. First, I'll read the question. A bar of length L tapers uniformly from diameter 1.1 d at one end to 0.9 d at the other end. The elongation due to axial pull is computed using mean diameter d. What is the approximate error in computed elongation? Okay, so this is the question. Now I will analyze the question. A taper bar of length L is being subjected to an axial load P. The axial load P will tend to pull the taper bar, due to which the taper bar will undergo deformation. Therefore, the actual deformation value should be calculated by considering the values of bigger end diameter of the taper bar and smaller end diameter of the taper bar. But in this question, they have calculated the deformation value by considering the value of mean diameter of the taper bar. Therefore, the deformation value, that is, the calculated deformation value, is wrong. So in this question, we have to find the value of percentage error, which means we have to find the percentage difference between the actual deformation value and calculated deformation value. To be more precise, we have to find whether the calculated deformation value is more than the actual deformation value. If it is more, how much percentage will it be more? Or the calculated deformation value is lesser than the actual deformation value. If it is less, how much percentage will it be less? So this is what we have to find here. Now I will list out the given conditions from the question. L is the length of the taper bar. E is the Young's modulus of the taper bar. D is the mean diameter of the taper bar. D1 is the bigger end diameter of the taper bar, which is 1.1 D. First of all, what is this 1.1 D? The meaning of this value is the bigger end diameter of the taper bar is 1.1 times more than the mean diameter of the taper bar. Okay. D2 is the smaller end diameter of the taper bar, which is 0.9 D. And the meaning of this value is the smaller end diameter of the taper bar is 0.9 times more than the mean diameter of the taper bar. Okay. And P is the load applied on the taper bar. So friends, by using these 6 conditions, we are going to find the value of percentage error or percentage error in the deformation values. Okay. Now I will move to the solving technique. First, we will find the calculated deformation value, which is taken as DL calculated. As I said earlier, the deformation value is calculated by considering the value of mean diameter of the taper bar. Okay. So the area of the taper bar formula will be A is equal to pi by 4 into D square. Okay. Now we will write down the formula of calculated deformation value, and the formula is DL calculated is equal to PL by AE, where P is load applied on the taper bar, L is the length of the taper bar, A is the area of the taper bar, and E is the Young's modulus of the taper bar. So in this formula, A is pi by 4 D square. So the next step will be DL calculated is equal to PL whole divided by pi by 4 into D square into E. Now in this RHS, bring this 4 to the numerator, because we have an arithmetic formula, and the formula is A whole divided by B by C is A into C divided by B. Okay. Therefore, by considering this formula, we can move this 4 to the numerator. So the next step will be DL calculated is equal to 4PL whole divided by pi D square E. So friends, this is the calculated deformation value of this taper bar. Okay. Now we will find the actual deformation value, which is taken as DL actual. As I said earlier, the actual deformation value is calculated by considering the values of bigger end diameter of the taper bar and smaller end diameter of the taper bar. Therefore, the formula for area of the taper bar will be A is equal to pi by 4 into D1 into D2. So in this formula, we know we know the values of d1 and d2. So just substitute the values. We get a is equal to pi by 4 into 1.1 d into 0.9 d. So in this RHS, 1.1 d into 0.9 d is 0.99 d square. So the next step will be a is equal to pi by 4 into 0.99 d square. Okay, now we will write down the actual deformation value formula, and the formula is dl actual is equal to pl by ae, where p is load applied on the taper bar, l is the length of the taper bar, a is the area of the taper bar, and e is the Young's modulus of the taper bar. So in this formula, a is pi by 4 into 0.99 d square. Okay, so the next step will be dl actual is equal to pl whole divided by pi by 4 into 0.99 d square into e. Now in this RHS, bring this 4 to the numerator. We get dl actual is equal to 4pl whole divided by pi into 0.99 d square into e. So friends, this is the actual deformation value of this taper bar. Okay. So we have found out the actual deformation value and calculated deformation value. Now it's time to find the percentage error of the deformation value. Before finding the percentage error of the deformation value, first we will write down the basic formula of percentage error. And the basic formula is percentage error is equal to calculated value minus actual value whole divided by actual value into 100%. Now I am going to modify this formula according to the deformation value. Therefore, the percentage error for the deformation value will be percentage error is equal to dl calculated minus dl actual whole divided by dl actual into 100%. Okay. So in this formula, we know the values of dl calculated and dl actual. So just substitute the values. We get percentage error is equal to 4pl divided by pi d square e minus of 4pl divided by pi into 0.99 d square e whole divided by 4pl divided by pi into 0.99 d square e into 100%. Okay. Now take 4pl divided by pi d square e as common term from numerator and also from denominator. We get percentage error is equal to 4pl divided by pi d square e into 1 minus of 1 divided by 0.99 whole divided by 4pl divided by pi d square e into 1 divided by 0.99 into 100%. Okay. Now in this RHS, 4pl divided by pi d square e and 4pl divided by pi d square e gets cancelled. So the next step will be percentage error is equal to 1 minus of 1 divided by 0.99 whole divided by 1 divided by 0.99 into 100%. Now in this RHS, take LCM in the numerator. We get percentage error is equal to 0.99 minus 1 divided by 0.99 whole divided by 1 divided by 0.99 into 100%. In this RHS, 0.99 minus 1 is 0.01. So the next step will be percentage error is equal to minus 0.01 divided by 0.99 whole divided by 1 divided by 0.99 into 100%. Now I am going to modify this RHS by considering arithmetic formula, and the formula is a by b whole divided by c by d is a into d divided by b into c. So similarly, minus 0.01 divided by 0.99 divided by 1 divided by 0.99 will be minus 0.01 into 0.99 divided by 0.99 into 1. Okay. So the next step will be percentage error is equal to minus 0.01 into 0.99 whole divided by 0.99 into 1 into 100%. In this RHS, 0.99 and 0.99 gets cancelled. So the next step will be percentage error is equal to minus 0.01 into 100%. So minus 0.01 into 100% is minus 1%. So the next step will be percentage error is equal to minus 1%, which means the percentage error of the deformation value is minus 1%. In this percentage error, the negative sign indicates that the calculated deformation value is lesser than the actual deformation value. and the calculated deformation value is 1% lesser than the actual deformation value. Okay, so friends, this is the answer for this question. I hope you all would have understood. If any doubts are there, please do comment in comment box, and remember to like, share and comment on our videos. Thank you friends.